Okay, our next speaker is Meike Hatzel, who will be speaking on Erdős-Pósa property for tripods and directed graphs.
Thank you. So the result I'm presenting is joint work with Marcin Brianski, Karolina Okrasa, and Michał Filipczuk, colleagues from Poland I work with. And you've already heard a lot about Erdős-Pósa. I'm just going to repeat a few things. So because Ojang already mentioned the result by Erdős-Pósa from 65, that in a graph given, you can either find a lot of disjoint cycles, or you can find a small set, such that if I delete the small set, then my graph will not have any cycles at all. So this can be considered for all kinds of cycle-like things, as Ojang already mentioned, but it can also be just used for any kind of subgraph. And then we call it, because of this initial result by Erdős-Pósa, we call it for a subgraph to have the Erdős-Pósa property. So either I find the subgraph, find a lot of disjoint copies of the subgraph, or I find a small set, such that if I delete this set from my graph, I cannot find any copy of the subgraph at all. And if I step away from this phrasing a little bit more, I can also consider things that are a little bit more general, as, for example, the Menger theorem, which I here state in the directed graph version, because we're going to use it later for directed graphs. If you dislike that, just ignore that's on directed graphs. It's still the same theorem. Here I have fixed sets A and B in my graph that I'm giving in advance. And then I ask from paths that start in the one set and end in the other set. And Menger proved that either I can find a lot of these disjoint paths, or I find a set that destroys all of these disjoint paths. Actually, the set is like, if I cannot find k path, then I have a set of k minus 1. So this is really tight property there. And this somehow also is an Erdős-Pósa property, because I can rewrite this and say, so the graphs from A to B in my do have the Erdős-Pósa property. But then I also have to be given these sets A and B. And the result I want to talk about is a little bit along these lines. We consider something that's a slight generalization of what a path would be. We consider a digraph that is given with a fixed set of sources and a fixed set of sinks. And now I want to pack something that I call a tripod. This is a collection of 3 paths. 2 of them start in my set of sinks, and then they end in a common vertex. And the third path then starts in this common vertex and goes all the way to a vertex in the set of sinks. So 2 source to center paths, and then 1 center to target path. And this we call a tripod, because it has 3 legs. And this is slightly more general than paths are. And we want to prove that those have the Erdős-Pósa property. Means we can find a function that whenever I give you a graph and a fixed set of sources and a fixed set of sinks, either you can find these vertex disjoint tripods between these 2 sets, or you have this set of bounded size that intersects all the tripods. So if I delete it, I will not have any tripods left. And this is really interesting, because if we look at these Erdős-Pósa results, there's a bunch of them. But normally, as soon as we go to directed graphs, things get super complicated. So a lot of things that turn out to be kind of straightforward or easy on undirected graphs often are either unintuitively wrong or really hard to prove, or even worse, both, actually wrong, and it's hard to see that they're wrong. So this is why, specifically for acyclic structures, this is a very interesting topic to look at. For strongly connected graphs, there's a characterization by now for having Erdős-Pósa theory properties for directed graphs. But for acyclic patterns, there's really few results there. And the one result we have, the Menger theorem, is like omnipresent. We use it all the time. And specifically, we kind of needed this for a different project, so we are personally also very interested in this. Now I have good news. If you do not really like digraphs, we do get around most of the messiness normally digraph proofs bring with them, because we kind of just steal the work of other people who did the hard parts and then ensemble them and actually get a really nice proof for this theorem. And I'm actually going to present the whole proof, because we can. And I'm using two major, sorry, yes?
You have a bound on the size of that.
Yes, but it's not nice, so I'm not actually going to talk about the function. So there is a bound, but it's an exponential tower of things, as it always is for directed graphs. So there is a function, and I will talk about there are functions, but I will never actually give a specific function. Especially as the thing that blows up our function most is one of the black boxes we use. Okay. Exactly the first black box we use. Because I'm gonna prove two things first, two lemmata I need. The crossing lemma is I identify a certain situation in which I can find a large packing of tripods first. And I use a concept called onions for this that most of my co-authors used in a different project, and it turned out to be really helpful for this. And then in the second part, I prove something I call the partition lemma, means where I can partition my sources into two parts, and then kind of also find a partition of the targets in a really nice way, such that I can hit all the paths that cross over this partition. And then I can only have to look at the one side and then the other side. And this just allows us to apply very standard techniques for proving Erdős-Pósa proofs by first separating it into two parts and then inducing on both sides. We will get there. So first, we will do these two lemmas on the way. And the first one uses something called onions. An onion, obviously this is an onion, we just have to squint a little, come on. I have two vertices, a root and a stem, and then I have two paths in one direction and one path left. So this is called an onion. And then if I take a lot of onions and identify the root of them, then I get an onion star, which looks like a star with onions coming off it. And you can read the text, we can also ignore it. It's just a lot of onions that have either the root or the stem, and like half of them are outgoing, half of them are ingoing. Actually, for what I'm using, I only need that they're outgoing anyways. So what my colleagues proved is, what do you do with onions? You harvest them. So they identify a situation in a digraph in which you can find a lot of these onions, or a large onion star, to be more precise. And what do I need for this? I need a vertex that is kind of the center of all of this onion star. I need a large family of paths that starts in this vertex, and I need a large family of paths that end in this vertex, and if they intersect a lot, then it's actually not surprising that if you sort this out, you get an onion star, but it's actually a lot of work, and the function is really hard, because directed paths and intersecting just really hard to sort out. Anybody who's ever done it in a proof knows, nightmare. So we're doing this, and don't do it ourselves, just use this. And we are gonna take this result and infer our crossing lemma from it, which is now we don't take a single vertex or anything, we just take a set of paths that all start in my set of sources, and then another set of paths that are all disjoint that all end in the set of things, and I say, now this contains a lot of tripods. And I want to use the onion harvesting lemma to prove it. So first thing I do, I need some vertex x. The onion harvesting lemma, somehow you needed a vertex. And then I link it up to all the sources and add edges from all the things to my x. So now I have these collection of paths that all start in x, right? I just prolong everything in k by this extra edge. And then all of these paths, if I prolong them by this extra edge to x, end in x. So this now makes my onion lemma applicable, so I can find a large onion star in it. And if I look at something that is an onion starting in x, going through this, then I can easily identify this part that did lie in my original graph, and this is a tripod. Now you will say, okay, but you kind of cheated us there because the onion lemma, can I also go back? Yes. The onion lemma said this is edge disjoint, right? We wanted to pack things vertex disjointly. But actually with a little trick, by just splitting every vertex into an edge, and every ingoing thing goes to one vertex, and every outgoing thing goes from the head of this edge, we can just differ between these two settings. So actually on directed graphs, often edge disjoint and vertex disjoint, not that different. So we can still do that with a kind of extra technical step in the proof. So now I have that if I have these two linkages, one starting in the sources, one ending in the things, and they intersect a lot, then I find a large packing of tripods. Step one. What I can also do is if I now look at my linkages not starting in the one and ending in the other, but I take two linkages that both start in different sets of sources and end in the same set of things, then I can still find a large packing of tripods. So I have these two linkages, and these can intersect however they want. But if they end in the same set of things, then they contain a lot of tripods. To prove this, I name for every vertex in my set of things the path of the one linkage ending in this vertex by py, and the path in the other vertex ending by qy. And now I keep this here at the side so you can remember how I named this. Now I build an auxiliary dry graph on the vertex set y. And I add an edge between two vertices in y, and it's a directed edge, right? So if the p path of the first vertex intersects the q path of the second vertex, then I add an edge. Now I have a large digraph. Because I start with a large set and large linkages, I have a large digraph. Now I apply Ramsey's theorem if I have a large graph to the underlying undirected graph, actually. So I either have a clique or an independent set. If it's independent, it's also independent in the directed sense. So let's consider that case first. So now I have these two linkages here, and I have a large subset of these vertices such that they are independent. So neither P intersects Q for any pair, nor the other way around, right? So I don't have any edges between these. So if I look at the two paths ending in the same vertex, they do contain a tripod. And as I have that these are an independent set, and the P's come from a linkage, so they don't intersect, and the P doesn't intersect any of the Q's because it's an independent set, I can just take these tripods, get a large packing. So if I have an independent set, in that case, I'm actually very happy. So assume I have a large clique. Now I consider that I actually did build a digraph, which means if I have a large clique, it's a large semi-complete graph. So if I delete a few edges, I have a large tournament in it. And then it's a known result if you work with tournaments, if you just take this large enough, actually 2 to the, take some constant that you want, then you get a constant size transitive tournament in this. If you just make your tournament large enough, eventually you end up with a transitive sub-tournament. And this means I can order the vertices of this transitive sub-tournament that I found in Y, and all the edges go from left to right. So if you don't know what a tournament is or what it means to be transitive, I have the set of 2L vertices, and all the edges go in that direction. And all the edges are present. So between any pair, I have an edge and always goes right. So now I split this into 2 parts and take the path that end from P that correspond to the first half, and the path from Q that correspond to the second half. And what does it mean that there's an edge from here to there? Means that the P path ending in this vertex intersects the Q path ending in that vertex. Which means that now I have two large linkages, two large collections of paths that pairwise intersect. So by my crossing lemma, I get, again, a large packing of tripods. Which means that it suffices that I have these 2 linkages that start in different parts of the sources and end in the same sync set to get a large collection of tripods. Yeah, by crossing lemma. So let's formalize this a little bit more. So that means if I take a subset of my sinks, and I look at the now if I take a subset of my sources and I look at the things that the sets of the sinks that I can reach from this, I call this linkable. I cannot have a large set of sinks that are linkable from 2 different sets of sources, because then I would get these 2 linkages that allow me to find a large packing of tripods. So that means, however I partition my sets of sources, the maximal set that is linkable for both is of bounded size, or I get a packing immediately. So now I want to use this to prove that whenever I start with a partition of my sources, I can find this partition of the targets in a way that I can find a hitting set of this crossing paths. A picture will follow if you do not if you're not sure what this means. So, and to prove this, I want to use Matroids, right? I had to do something with Matroids. And they help us a lot with this. So means if I look at the set of sources and consider all the possible subsets of targets that are reachable by a large linkage, then this builds a Matroid on the ground set of all sinks, which is called a gamoid and was defined by Hazel Perfect in 1968. So we were like, great, we don't know anything about Matroid theory, but if it helps, that's good. So if I take a partition, the 2 parts of my partition give me 2 different Matroids that work on the same ground set, the ground set of all sinks. And I also found a bound how large maximally an independent set can be that's independent in both of these Matroids. Right? And I guess you're the Matroid theorists, but you will immediately be like, yeah, sure. So you can use the Matroid intersection theorem. it took us a little bit longer to figure out that this is actually good and helpful, but eventually we also got there. And so to prove this partition lemma, we now we take a partition, we take the two gamoids, and we have this bound on the maximal cardinality. So the Matroid intersection theorem gives us, we can partition the sinks as well in a way that these two terms add up to this bound that we had on the size of the independent set. Okay, so what does this actually mean? If I look at the rank in the Matroid induced by the first partition, looking at the second part of the sink partition means that's the number of disjoint paths I can find from S1 to T2, so crossing over this partition to the wrong way. And so by Menger's theorem says if I have a number of maximal paths that I can have there, then I can also find a hitting set for any larger set of paths. So I can find a hitting set of size this plus 1, of this size, that hits all the paths from S1 to T2. And the same way I can also find a set of the rank where I switch the two indices to hit all the paths from S2 to T1. And now, one of these might be large, but I know that the sum of these is L. So if I take the union of these two paths, then I find a hitting set that hits everything going, crossing over this. So this establishes this partition lemma that I wanted to prove. And as I apologize, this slide has really little pictures, but it didn't fit next to it. I just repeat what we now have in picture form. So we have the two sets, sources and targets, and we split the sources into two. Then we obtain a split also on the targets in a way that if I look at all the paths that go between the two partitions, so crossing over, I find a set that hits all of these. So if I delete the set, afterwards there's no paths that cross in the wrong direction. That's what this partition lemma gives us. So, to get back to what I actually want to prove, now I established the two tools I needed to do this. Remember, we actually wanted to pack tripods. So we prove this by induction over the number of tripods I pack, and I assume we cannot pack them, because if I find a large packing, then I'm done. But as we saw with the partition lemma, that if I assume there is no large packing, that I can get these certain properties on hittings and partitions, so that's nice. So I assume there is no such hitting, no such packing for tripods. So by my partition lemma, whenever I now consider some partition on the sources, I also get a partition on the targets, and I get a hitting set that hits all the crossing paths. And additionally, I also define two new digraphs, kind of the top and the bottom digraph, where I restrict my source and target set to the top sources and top sinks, and the bottom sources and the bottom sinks. And an important observation to make is, if I have a tripod in the one and a tripod in the other, they can never intersect. Because in both of these graphs, I have already removed f, and however I managed for two tripods to intersect, they will always give a path that crosses over. Maybe you have to think about it a little bit, but you'll get there. Or you just believe me. So if I have tripods in the two graphs, they cannot intersect. So now suppose I find a partition where both of these graphs have at least one tripod. Then I claim that also both of these paths have at most k minus 1 tripods. Actually, less than, yeah, okay. it says less than, good. Less than k minus 1 tripods, because otherwise, as they cannot intersect, I just combine them, I find a large packing, I'm happy. So I actually have less than k minus 1 tripods, which means that now to both sides, I can apply induction and find a hitting set for tripods on both sides, and then I add F, and then I have a hitting set for all the tripods there are. So as soon as I have a partition such that both sides contain at least one tripod, I actually find my tripod packing, or my hitting set. So now we can assume that all the partitions we have actually have an empty side. Either D1 or D2 does not contain any tripods at all. And let's say S1 is the empty side. Then we choose S1 as the empty side maximally. So there's no partition having a larger empty side. Then I take a vertex from S2, because if S2 would be empty, I would be done. There is no tripods after deleting F. And I move it to the other side. I take the new partition, just differing by this one vertex. Then I get new choices of my hitting set for the crossing paths and everything on the right. But what is interesting is that if I consider this, then F actually hits all the tripods starting in S1. So if I now consider this, now as this was chosen maximally, I have to have that in this new partition, the lower side is empty. Meaning that in the new partition, the lower side hits all the tripods starting in S2 prime. So now if I take the union of these two hitting sets, they hit all tripods, because I have a hitting set that hits all the tripods that start in S1, and a hitting set that hits all the tripods that have a source in S2 prime, and they only differ by one vertex, but every tripod has two sources. So every tripod has to have a source that such that I already hit it with my two hitting sets. So this finishes the proof of the main theorem by this very standard technique of just finding the separation and looking at the two sides. And either I can combine packings on both sides, or I can apply induction on one. And there's one extra trick of moving one vertex. Okay, questions? Yes.
Can we generalize the method for not only tripods, but I don't know, quadrupods, where like three sources come here, three sources begin in one sink, because I think we can use like more bigger onions and the same method. So I want to know what's so special about tripods.
So special about tripods is that you can use the onion stars. But if you would want it for larger quadruple pods or whatever, then you would need an onion harvesting lemma with more layered onions. And the onions always go two paths in one and one path back. So if you wanted to do that, you could not do it as lazily as I did in this case, but you would actually have to look into the onion harvesting lemma and generalize that one first. But if you can generalize the onion harvesting lemma, then I think the chances are quite good that you can also get. And if you ask me whether I believe they have Erdős-Pósa property, then yes, I do.
Is there hope that in the planar graphs, can you get a better bound?
I don't know how the onion harvesting lemma is proved in detail. So I would guess yes. Because as far as I remember, I mean, I did read the proof at some point, but it's a while ago, so I do not know by heart. But I'm pretty sure that you can do so they have a lot of technical part on this, sorting out different paths that intersect, and usually this becomes way easier in planar directed graphs. So my expectation would be on planar graphs, the proof is still the same, this part, and you would just, okay, you would have to get rid of the Ramsey part. But so I guess the onion harvesting lemma, the answer has to be yes. And the yeah, you would have to replace the Ramsey part by a different argument, but it would be also that would become polynomial.
Any further questions? Then let's thank our speaker.